Okay guys, in this video I'm going to work through just a couple of examples of solving not just a polynomial inequality but a rational function inequality, which is in and of itself having to deal with polynomials. So let's take a look at number 25 here. And actually what I want to start with is just this, again, this idea that before we do anything here, what I want to do is I want to get a 0 on one side and I want to factor the non-zero side if at all possible, at least the top and the bottom of this expression. So one thing that I notice is that the top is unfactorable, at least it only has a GCF of 1, and the bottom is also unfactorable. So this, for what it's worth, is already in its factored expression. So in order to find our critical values here, where would they be? Well, keep this in mind. By getting a 0 on this side right here, we're saying that this function on the left here, this non-zero expression, is really just a function of x. And so what we're looking for is where the x values lie that cause our y values or our function values to be either greater than 0 or equal to 0. So what I did was actually went and got a picture of this graph on my graphing calculator here. And what I want to point out to you is really that we're looking for all of the x values that cause my function to be above the x-axis or greater than 0 or equal to 0, so on the x-axis. And what I notice right here is that my function is above the x-axis until we get to right around here, which I'm not really sure what this 0 is right here, but you can tell it crosses into negative territory. And then when we get to this, which is our vertical asymptote, it goes back to being positive again. So what I really want to point out is essentially that our critical values on a rational function are at the zeros of the function. That is to say that you can see that we go from having positive to negative y values when it crosses over the x-axis. But I also want you to notice that our function goes from having negative y values to positive y values wherever we have a vertical asymptote. So with respect to the critical values on a rational function, one thing we want to acknowledge is this. The critical values for a rational function must occur at both the zeros of the function and at the vertical asymptotes of the function. So here's what we're going to do, essentially. We're going to find the zeros and the vertical asymptotes of this function. And the neat thing about that is, essentially, the zeros of the function occur when the top equals 0, and the vertical asymptotes of the function occur when the bottom equals 0. So let's go ahead and do this. We're going to write down our critical values here. And so with respect to our critical values, I suppose that 2x plus 1 equals 0 if and only if x equals negative a half. And I would say that the denominator here equals 0 if and only if x equals 3. So our two critical values are these values right here, and just like I've done in any of the other examples that we've already looked at, I'm just going to go put these critical values on our number line to set up our test intervals. So what I know is that looking at this, I suppose that I've got a negative and a positive critical value, so I'm going to put 0 kind of in between here. How about we'll call this like negative 1. We'll say 1, 2, 3. We'll call this 3 here. So our critical values, when we highlight these, we're going to say I've got 1 at 3, and I've got another 1 at negative a half, which is right here. So with respect to our test intervals, let's go ahead and set up what these test intervals would be. And, oh cool, let's try that again though. I don't like that color. How about this one? Orangish. Our test intervals are going to be, excuse me, everywhere on the number line between and around these critical values that you see here. So setting up our test intervals, because I have two critical values, as is typical, I'm going to have three intervals. So my first interval is from negative infinity to negative a half here. Our second test interval is from negative a half up to our next critical value, which was 3. And our last test interval was from 3 to infinity. And so as we typically do, all we're really going to do is we're going to pluck some x values out of each of these intervals here, and we're going to go plug them back into our factored original expression up here to see if we get a true or false statement. So to the left of negative a half, man, I have to go with negative 1 here. If I am between negative a half and positive 3, I definitely have to test 0, otherwise I'm crazy. And to go to the right of 3, I think 4 is probably a good option. So we are going to test these. Recall that we are going to test them into the original factored expression. So what I get is this. I get 2 times negative 1 plus 1. And this is all over negative 1 minus 3. And this is supposed to be greater than or equal to 0. So what I end up with on top is negative 2 plus 1, which is negative 1. On bottom, I get a negative 4 greater than or equal to 0. And the neat thing about this is all I cared about was that the left-hand side comes out to be a positive. So if that's the case, then this is actually true, which is a great thing because it means that we've stumbled across one of our solution intervals. Now, when we test 0, we say 2 times 0 plus 1. This would be 0 minus 3 in the denominator greater than or equal to 0. I get this 1 on top and negative 3 on bottom greater than or equal to 0. But in other words, I got a negative was greater than or equal to 0, which is false. So if that's false, okay, then what I know is that nothing on that test interval can also be a solution if 0 wasn't a solution. And then to the right here, we say from 3 to infinity, we'll test an x value of 4. So again, we'll plug this back into our factor expression, 2 times 4 plus 1. This would be 4 minus 3 greater than or equal to 0. But what I get is 8 plus 1, or 9, over 4 minus 1, which is 1, greater than or equal to 0. And last time I checked, a positive divided by a positive is a positive. So a positive is definitely greater than or equal to 0, meaning that we get a true statement here. Okay, so I'm going to put a box around this. Now, so here's the thing. Now we have to come up with our our solution intervals, but we also have to come up with the graph. And so one thing to keep in mind is this, when we talk about solutions here, okay, and maybe we make a note here, and I'll even type this out because it'll be faster and my handwriting is much better. We say exclude any endpoints of solution intervals if they occur at a vertical asymptote. So essentially, what we're saying is this. Of our critical values that we had listed here, this one right here corresponded to the zeros of the function, would cause the top to be equal to 0. And so if I were to say plug in negative a half into this function, I do get 0, but 0 is greater than or equal to 0. So I would actually have to include this negative a half right here when we list our solution interval. And we'd say from negative infinity to negative a half, and we should include negative a half because it is a 0. When I plug it in, I get 0, and 0 is greater than or equal to 0. But should I include this 3 that I saw right here on this interval? Now, if I plug in 3, the thing I want you to notice right off the bat is you get 3 minus 3 in your denominator, which is 0. In other words, you get 0 on the denominator, which is undefined in the expression, and undefined cannot be greater than or equal to 0 because it is simply undefined. So, again, excluding any endpoints of solution intervals if they occur at a vertical asymptote basically mean that if you look at your test intervals here, this interval worked and 3 was at a vertical asymptote. So when we write our solution interval, we're just going to say from 3 to infinity. And in terms of what this graph would look like, we would say that everything to the left of and including negative a half, but everything to the right of 3 but not including 3. So here would be our solution intervals, and this would be our solution graph. Cheers.